Now let's develop a comprehensive model of the camera so that we can calibrate the camera. For this, we're going to discuss what's called the forward imaging model, which takes you from 3D to 2D. So here is the setup. We have a world coordinate frame W, shown right here. And let's say we focus our attention on a single point in this world coordinate frame. That point is P. In this world coordinate frame lies your camera, and the camera is defined by its own coordinate frame C, where the z-axis of the camera coordinate frame is aligned with the optical axis of the camera. And let's assume that the effective focal length, which is a distance between the effective center of projection and the image plane of the camera, is F, right here. So now, if we know the relative position and orientation of the camera coordinate frame with respect to the world coordinate frame, then we can write an expression that takes you all the way from the point P in the world coordinate frame to its projection xi on the image plane. That complete mapping is what we refer to as the forward imaging model. So here's what we're going to do. We start with a point in the world coordinate frame, xw. And then we're going to model its transformation to the camera coordinate frame. Remember that this is a 3D to 3D transformation from the point xw, which is in 3 dimensions, to the point xc, which is also in 3 dimensions in the camera coordinate frame. Once we have xc, we can then apply perspective projection to end up with the image coordinates, which are now 2D coordinates on the image plane xi. So this whole model, going from world coordinates to image coordinates, 3D to 2D, is what's referred to as the forward imaging model, and we're going to use it to develop a comprehensive linear model for the camera. So let's start with the latter of these two, which is perspective projection. We know perspective projection equations very well by now, so you have xi divided by f is equal to xc divided by zc. So we are assuming here that the point has been defined in the camera coordinate frame. And you have yi divided by f is equal to yc divided by zc. And we can rewrite these equations to get xi and yi. These are the coordinates of the projection of the point P onto the image plane. So now let's take a closer look at the image plane. So this is your image plane right here. And the fact is that we have assumed that we know the coordinates now in terms of millimeters. That is the same units that the point P is defined in the camera coordinate frame. But in reality, what we have is an image sensor, which is used to capture the image. And this image sensor, we know, has pixels. So we have pixels, and so we have pixel coordinates u and v, and we have to figure out the mapping from the image coordinates here in millimeters to pixels. In addition, we have to keep in mind that there is no reason to believe that the pixels are square. The pixels themselves could be rectangular. So the way we do this is by saying that there is a pixel density mx in the x direction, which is number of pixels per millimeter, and we have a pixel density my in the y direction. And so now we can say that the pixel coordinates of the projection of the point P are u and v, where u is equal to mx times xi, and v is my times yi. So we've gone from millimeters to pixels now. Remember that these pixel densities mx and my are unknown. They're a part of the calibration process. Okay, there's one more thing to worry about, which is thus far we have assumed that we know where the center of the image is, that 0, 0 pixels corresponds to the center of the image where the optical axis pierces the image plane. But there's no reason for us to believe that we know where that point is. That point is called the principal point. And in fact, when we capture an image, the coordinate frame of the image is usually located at one of the 4 corners of the image, say the top left corner right here. This is 0, 0. We don't really know where the principal point is. So we'll throw in the coordinates of the principal point as well as unknowns. We'll call them OX and OY. So now we have, to modify our perspective projection equation, we say U is equal to MXF XC divided by ZC plus OX, and a similar equation for V. So now we have a more complete model for perspective projection given by these two equations. One thing to note here is that you have mx times f. Remember, both are unknown to us, the pixel density as well as the effective focal length. So we can combine these into a single unknown, single parameter fx, and we can do the same with my times f, that's fy. And so now we have these two unknowns here, fx and fy, in addition to the location of the principal point, which is also unknown, ox and oy. So fx and fy, just a word about this, these can be seen as effective focal lengths in the x and y direction. Of course, we know that a camera typically has only one focal length, effective focal length, the distance between the center of projection and the image plane. But in order to accommodate for perhaps non-equal pixel densities in the x and y directions, the fact that pixels may be rectangular, we are going to say that we have perhaps different focal lengths in the x and y direction, right here. So those are your unknowns, and they are called the intrinsic parameters of the camera, fx, fy, ox, and oy. If we know these, then we know the camera's internal geometry. So one thing to note here is that we have a model, but it's a nonlinear model. And we know, you see that ZC is in the denominator here, and we know that it's always advantageous to have a linear model that makes the estimation process easier. So how do we go from a nonlinear model to a linear model? Well, sometimes it's possible to do this using homogeneous coordinates, which we've discussed in the past. So the homogeneous representation of a 2D point U, we know, is a 3D point U tilde, where the third coordinate, W tilde, is called fictitious. It is used for scaling or normalization purposes as follows. And we also looked at a visual representation of this. We said we can imagine that the UV plane is this plane right here, and in relation to this plane, we can define a coordinate frame, U tilde, V tilde, W tilde, such that the UV plane lies as at W tilde equal to 1. And now we can say that all the points that go from the origin, but not including the origin, go from this origin through the point UV. All of these points on this line L correspond to homogeneous coordinates corresponding to this point U right here. They're all equivalent to each other. You give me any point on this line L, and I can find from that the point U. So U can be expressed in homogeneous coordinates as UV1, and that's equivalent to the same multiplied by any constant, not equal to 0, any constant W tilde, and that gives you U tilde. So U is equivalent to U tilde. You can give me any one of these, I can give you the UV parameters or the pixel coordinates. So that's going from 2D to 3D. Now, if you're looking at a 3D point that's given to you, let's say, for instance, the coordinates of a point in the world coordinate frame or in the camera coordinate frame, that is XC, YC, ZC, we can represent those as well in terms of homogeneous coordinates by using the following. You go from a 3D point, for any 3D point X, you can represent it as a 4D point X tilde, where now the fictitious coordinate is again W tilde right here. We're going to use this as well as we develop our linear camera model. So a point in your camera coordinate frame, three-dimensional point, X, Y, Z can be written as XYZ1, which is equivalent to the same multiplied by any constant W tilde. That gives you X tilde right here. These two are equivalent to each other in homogeneous coordinates. All right, with that in place, homogeneous coordinates, we can come back to perspective projection. So here you have the two equations we have been discussing thus far, and now we can express uv, the pixel coordinates, using homogeneous coordinates. We can say it's uv1, which is equivalent to uv1 multiplied by, say, zc. Any constant, let's make that constant zc. So it's zcu, zcv, and zc now. These two are equivalent. And why do we do this? Well, you can multiply this entire equation by zc, and you'll get zc times u right here, and something on the right-hand side, which is this. zc times v, that gives you this, and zc right here. And the reason we do this is because now we can further simplify this by using a matrix. And that matrix is this one right here, a 3x4 matrix that includes all the internal parameters of the camera. fx, fy, ox, and oy multiplied by the homogeneous coordinates of the three-dimensional point defined in the camera coordinate frame, xc, yc, and zc. Okay, so now this tells us that we have a linear model for perspective projection. And this matrix that we just introduced is called the intrinsic matrix. It has all the internal parameters. Just a couple of words about the intrinsic matrix. If you look at this submatrix right here, this block 3x3, we call it the calibration matrix K. And this matrix has a very special structure to it, which we should bear in mind because we're going to use it later when we solve for the various parameters. And the structure is that it is an upper right triangular matrix. You can see that these elements are non-zero, whereas these are zero. It's an important property that we will exploit later. And the whole matrix, like I said before, is called the intrinsic matrix M-int, which is a concatenation of K, this K matrix, and a column of zeros right here. All right, so you have M-int that takes you from a point, homogeneous coordinate representation of a point in the camera coordinate frame, 3D, to its pixel coordinates in the image, U tilde. All right, so we are done with perspective projection, and we ended with a linear model. So that's good. Now what we need to worry about is the mapping of a point from the world coordinates to the camera coordinates. That's 3D to 3D. So that can be done by using the position and orientation of the camera coordinate frame with respect to the world coordinate frame. The position, we'll say, is given by CW, a vector, and the orientation is given by a matrix R. Right? So, and this matrix R is what's called a rotation matrix. It is a 3x3 matrix, and the way one would interpret this 3x3 matrix is that the first row of this matrix right here is essentially the direction of this vector xc hat in the world coordinate frame. So the orientation of this vector in this coordinate frame is exactly equal to this. And the second row corresponds to the direction of yc hat, and the third row corresponds to the direction of zc hat. So that's your interpretation of your rotation matrix. But the most important thing is that the rotation matrix is special in that it's an orthonormal matrix. So let's take a look at what we mean by that. Two vectors, u and v, are orthonormal if and only if the dot product of the two vectors is equal to 0. So dot product of u and v is equal to 0, which means u transpose v is equal to 0, and the lengths of the two vectors is equal to 1, unit length. So examples of orthonormal vectors or sets of orthonormal vectors would be, for instance, the x, y, and z axes of a three-dimensional Euclidean space. So that would be an example. And an orthonormal matrix is one. It's a square matrix where the row vectors or the column vectors are orthonormal. And so for such a matrix, you have the inverse of the matrix equal to the transpose of the matrix. So that's the important property of an orthonormal matrix. The inverse is equal to the transpose. So R transpose R is equal to R transpose is equal to the identity matrix. And for our purposes, a rotation matrix is an orthonormal matrix. So now we can complete our transformation from world to camera coordinate frames using these extrinsic parameters R, rotation matrix, and the vector position CW. So what we do then is, let's say you're considering this point P, we can find this vector, this yellow vector XC in the world coordinate frame simply by taking XW minus CW, because it's all in the world coordinate frame. And then once you multiply that with the rotation matrix, then you have XC in the camera coordinate frame. So you have now mapped P from the world coordinate frame to the camera coordinate frame. We can expand this out and you get rotation matrix times XW plus a vector T, which is called the translation vector, gives you XC. And we can now write this out in matrix vector form as follows. XC we know as XC, YC, ZC. And here is your rotation matrix right here. Times XW, YW, ZW in the world coordinate frame plus your translation vector, TX, TY, TZ. So that's your mapping. And we'd like to do this using one matrix. For that, we can, again, bump things up using homogeneous coordinates. And now you have a mapping from the homogeneous coordinates of XW to the homogeneous coordinates of XC through a single 4x4 matrix that now includes both the rotation matrix as well as the translation vector. So you have your rotation matrix here, 3 by 3, your translation vector, which is 3 by 1, 0 and 1. So it's a 4 by 4 matrix. And this matrix is called the extrinsic matrix. So you have XW transformed to XC through MX'd, the extrinsic matrix of the camera. So with that in place, we have taken care of all the components. We have perspective projection, a linear model for that. Coordinate transformation 3D to 3D, we have a linear model for that. And so we can now figure out what is the mapping of a point in the world coordinate frame to pixels in the image. So here you have your mapping from world to camera using your extrinsic matrix. And here, so that takes you from XW to XC. And here, XC goes to UV in the image, pixels. So you're going from millimeters perhaps here in a world coordinate frame to pixels here. And so you go from XC to pixels, UV, using your intrinsic matrix MINT. And so therefore we can combine these two to get a direct mapping from a point in the world coordinate frame to a pixel location in the image. And that mapping is given by the product of MINT and MX'd, which is a single matrix P. And this matrix P is a 3 by 4 matrix called the projection matrix. So if we wish to calibrate the camera, all we need to know is the projection matrix. We need to find these 12 numbers right here, the projection matrix, and then we know the mapping. We can go from any point in 3D to its projection in pixels in the image. But what is even more interesting is you can go one step further, as we'll see later, by using the special properties of some of the matrices we've discussed. We can take this projection matrix and actually tear it apart into the intrinsic and extrinsic matrices as well.